Hello students, welcome again. I am Abhishek Kumar Chowdary, physics lecturer with Sri Chaitanya, Gosala campus. We were dealing with the nuclear physics and almost we finished the theoretical aspect of nuclear physics. We discussed each and every small detail that is required for your competitive exam. Now as I promised you, if you remember, and I hope you remember, that we are going to discuss the varieties problems. So I have collected the problems that have been asked in the NEET or JEE or some competitive exams and the problems which are generally doubt problems for my students. So the first problem to start with is a heavy nucleus at rest breaks into two fragments which fly off with velocities in the ratio given is 8:1. The ratio of radii of the fragment is, okay. See, in this question, first you have to deal with the basic concept there. What is the basic concept we are using there? The heavy nucleus at what? At rest. Okay. So from here, what information we are getting is the momentum initial is 0. Initial momentum is 0 for the heavy nucleus. And as the nuclear disintegration is not involving an external force there, so momentum here is constant. If you remember, we have discussed this concept initially. So if a heavy nucleus is splitting, what will happen? Momentum will remain constant. Fine. So momentum is constant. So can I write mass into velocity is constant, and from here can I write like velocity is inversely proportional to mass? Fine. And obviously mass, one concept if you remember, mass, atomic masses of almost all the nuclei were the integral multiple of mass of hydrogen atom. This was the concept on the basis of which we generally take mass number as the atomic mass unit. So here it is inversely proportional to A also, as mass is taken as A. Okay. Now V and A relation is there. But in question, what is required is the ratio of radii of the fragment. Now what we will use? The radii of the nuclei. And formula for that, if you remember, was R is proportional to A raised to power 1 by 3. R is proportional to A raised to power 1 by 3. So now A is to be related to R. So cube root of R is here. Cube root of A is R. So cube of both the side will give you R cube as A. Here A is given, so can you write, see here, can you write velocity inversely proportional to R raised to power cube? And from this relation, if velocity's ratio is 8:1, inverse is there. So obviously it will be 1:2, the cubic root of 8:1, and inverse proportion that would be 1:2. What do you have to take here? 1:2. Numerical calculation are not there much to learn here. What you have to learn here is if a heavy nucleus is splitting, what you have to do? You have to do the momentum conservation. Okay. Now moving to the next question. See, this is the question. This question, a large one, a huge one, but based on a very basic concept. But I have taken this question as this question is frequent doubt with the students. See, this question was basically from IIT 93 and so old question from IIT, a very guess question for your NEET examination. See, first read the question. A star initially has 10 raised to power 40 neutrons. Fine. It produces energy via, this is the reaction given via which, you can read the reaction properly, this is the reaction via which the star is producing energy. Fine. If the average power radiated by the star is 10 raised to power 16 watt, my dear future doctors, what is given? 10 raised to power 16 watt joule per second. This much energy in 1 second. This star is radiating. The deuteron supply of the star is exhausted in a time. This basically the options are asking you the order of magnitude of that time. So first get the question. There is a star. Fine. There is a star. It has initially 10 raised to power 40 deuterons, and there is a reaction given via which the star is producing what? It is producing energy. Fine. Now average power radiated by the star is given. Average power, get it very clear, joule in 1 second. So the question is asking you, Initially, so much number 10 raised to 40 deuterons was there. So in how much time that supply is going to get exhausted? Okay. Now moving to the question, some information. Datas are also given. The masses are given here. Options, there are 4 options. You have to take it out. Fine. See, first in this reaction, energy is to be calculated here. How will you calculate this energy? You will calculate energy by none other method than delta M. So delta M into C square, or delta M in atomic mass unit is given, so it is to be multiplied with what? It is to be multiplied with 931.5 megaelectron volt. So delta M you can calculate from the reaction as mass of all the quantities involved is given. You know how to calculate delta M, mass of reactant minus mass of product here. So delta M is to be calculated, and delta M into C square if you will do, you will get this much of energy. This was delta M into C square as the unit is joule. This much energy is being created. Now what is the power? 10 raised to power 16 watt, joule in 1 second. So see, 1 second, how many deuterons are there? Initial number of deuterons for power, not initial number, for power. This is 10 raised to power 16 joule in 1 second. So number of deuterons used is 10 raised to power 16 upon this energy delta M C square. Okay, this energy 10 raised to power 16 is the power upon energy. So much, suppose, so n number of deuterons are there. So n number of deuterons are giving this energy. So how much to reach this energy 10 raised to power 16 joule in 1 second? How many deuterons are required? This. Now what is the time taken? What is the total number of deuterons? Total number of deuterons is 10 raised to power 40, and how many deuterons are required in 1 second? I'm saying 1 second because power is the energy in 1 second. So 1 second, this much is the number of deuteron, right? So what is the time, total time for 10 raised to power 40? Just divide it and you will get your time. Clearly from here you can see the order of magnitude is 10 raised to power 12. So look for the answer. Where is 10 raised to 12? 40 minus 28. This is the answer. So first, energy, second, number of deuterons in 1 second, and third, total initial number of deuterons divided by the number of deuterons in 1 second, we get the required time. So we have done 2 questions. First, one on momentum conservation when the heavy nucleus splits, and the second was the delta M C squared and number of deuterons existing in time watt. Okay. Now if you remember, we have done a concept based on pair production and pair annihilation. Pair production. What was happening there? Energy was being converted into mass. And pair annihilation, 2 masses antiparticles are reacting, combining, annihilating each other, completely producing energy. So now we are going to take one question on such concept of pair production, annihilation. In this we are solving one question. Important topic, we'll note it down, make a star mark here. Important topic. Okay, let's see. First, what is the question? An electron-positron, you can see electron-positron pair is produced when a gamma ray of energy this much passes close to a heavy nucleus. Fine. There is a gamma ray and this is electron-positron pair is produced. What is this? This is pair production. Nice. Find kinetic energy carried by each particle produced and also find total energy with each. Okay, let's see what will happen here. See, what is the energy of gamma ray, the photon? The energy is 2.36 mega electron volt is the energy. Fine. Now this energy of gamma is producing electron-positron pair. So first m naught c square plus kinetic energy of electron. Okay. Rest mass energy m naught c square, the energy equal to mass plus kinetic energy of electron. Okay. This concept, if you remember, some energy is being supplied and some energy is used up as the mass equivalent, and if some energy is left there, that is being used as the kinetic energy of the pair production, that is electron and positron. Second, the same way for positron also, m naught c square plus kinetic energy of positron. Okay, so 2.36, first rest mass energy, the mass energy equivalent of the mass there, and then if some energy is left, then it will be kinetic energy of electron. In the same way, m naught c square for positron and then kinetic energy of positron. This is the main equation that needs to be solved further. Now we can write 2.36 is equal to 2m naught c square plus kinetic energy of electron plus kinetic energy of positron. And this energy, that data you should remember because you won't have much time to solve there, and I have given you the detail of this data. We have a good discussion of this data. It was 1.02 mega electron volt. You can recheck with the topic pair production and pair annihilation. Okay, so this is 2.36 minus 1.02. This is the value of 2m naught c square, 1.02. This is equal to kinetic energy of electron and kinetic energy of positron, but these two energy of electron, positron in pair production are almost equal. So these two are equal. Can I write it divided by 2? And this is kinetic energy of electron as well as kinetic energy of positron. This is the energy for them. But do remember, here we are dealing what? We are dealing the kinetic energy. You can see, find kinetic energy carried by each particle produced. This on calculation, kinetic energy will be around 0.67 mega electron volt. This is the kinetic energy. So we have just now calculated this. Again, question is asking you the total energy. Now this is for you to get clear. In pair production, there are two energies. One energy is what? One energy is there for? One energy is there for the kinetic energy, and second energy is there for the mass energy. So mass energy and kinetic energy, these are the energies. Kinetic energy is this. What will be the total energy? Total energy that you have to calculate, that would be 0.67 plus half of this, 0.51, and this will be what? This is 1.18 mega electron volt. This data you can use also. This is the total energy, and 0.51, that was the kinetic energy. And this is a very simple but very conceptual important question on the basis of pair production. Now moving to the next question, almost on the same line, a little change is there. We will notice what that change is. A gamma ray annihilates to produce a proton antiproton pair. This question is on the basis of annihilation. Who is annihilating there? The gamma ray, the photon, the energy, and what is being produced there. So gamma ray is annihilating and proton is producing. So pair production is also there. Annihilation is there for gamma. So gamma is annihilating to produce proton antiproton pair. If rest mass of each particles involved is given, see this rest mass. This is for proton and antiproton. This is going to produce a very significant amount of energy on the basis of mass energy equivalence. See, electrons mass is very less. So that energy produced over there was 1.02 mega electron volt, was again very less. But if proton antiproton pair is producing there, the energy is very high, because proton's mass is greater and greater mass is being converted into energy. Find how much kinetic energy these will carry. The question is almost on the same line. The only change is the mass energy equivalence will be very, very, very greater as compared to that of electron. Okay? See, what is the energy of gamma given? 1896 mega electron volt is given. Fine. Now this is equal to, again in the same way, m naught into c square for proton. Kinetic energy of proton. Mass energy, kinetic energy. Okay. Plus m naught c square plus kinetic energy of antiproton. Okay. Proton, antiproton. But this 2m naught c square is very high here. Kinetic energy of proton plus kinetic energy of antiproton. Okay. What is m naught c square? This is obviously m naught c square. In question m naught is given 1.007276 into 931.5 mega electron volt. This is it. And this is approximately equal to, let me write this for you, is 938 mega electron volt. Such a high energy there in proton antiproton. If you will compare to this that was producing an electron electron positron, that were 1.02 mega electron volt. See the difference, see the change. Okay, so this energy will be twice of this. So 1896 is equal to 2 into 938 plus twice of kinetic energy of either say proton or say antiproton, because their kinetic energy would be same. So 1896 minus this energy divided by 2, that is required in the question. The question is asking you kinetic energy of proton or kinetic energy of antiproton. And that would be 1896 minus 2 into 938 divided by 2, and this is approximately, if you can memorize the data, that would be 10 mega electron volt. This is the kinetic energy of proton. See, total energy is balanced for the gamma ray, so higher amount of energy is being converted into the form of m naught c square, so lesser energy is left there for proton, 10 mega electron volt. And what was the kinetic energy for electron positron? Being lighter one, obviously their kinetic energy will be greater, and that was almost equal to 67 mega electron volt. This is the difference in pair production of electron positron and proton antiproton. Important numerical, at the same time very conceptual discussion also. So we have discussed two questions on pair production annihilation process. In those questions, the important point was the total energy of the photon was equal to the mass energy as well as the kinetic energy. And I would suggest you to just memorize the data, like it was 67 in electron positron, 10 mega electron volt in proton antiproton, but the energy, mass energy of proton antiproton was much higher than 938 mega electron volt, much higher than that of electron positron. So these data are kind of fixed and they are not going to change. So if you will memorize this data by making the table, that will help you in future for your competitive examinations, and I hope you will memorize them. Okay, now we are moving to the next category of question, and if you will see a nuclear power reactor, see my underline points. We are doing this question on the basis of nuclear reactor. Do revise that nuclear reactor, and if you have already revised that, you remember there was a nuclear fuel first, and that nuclear fuel was generating some power. So first let me see in this question, what is the nuclear fuel? Okay, let's read the entire question. A nuclear power reactor generates electrical power of, oh my god, 100 megawatt. This much of a power a nuclear reactor can only generate. How many number of fissions occur per second? The frequency of fission per second is required in this question. If nuclear fuel used in the reactor is uranium, I found this. What is the difference? Why I was trying to find what is the nuclear fuel? Because if it is nuclear fuel, is uranium. If it is the uranium, you will have to memorize the energy 200 mega electron volt. You remember that? This is not given in the question, if you can see. This is not given. But on the data, that's why I focus on data, small data, fixed data in nuclear physics. Like mass of proton is the fixed data, or mass of neutron is the fixed data. So in fraction, I'm not telling you to be appropriate, be accurate with the 10th point of decimal, but 2-3 points it should be in your mind there. Here, uranium is a fixed nuclear fuel for the nuclear reactor fission, and for this, the energy released is 200 mega electron volt. So this is uranium. What is the energy? This is not given in the question, but I know by the concept of nuclear reactor and fission, this is 200 mega electron volt. Students, this is for one fission. Now suppose there are n fissions. So total fission will be what? N fission. So what is the total energy? Total energy is 200 mega, means 10 raised to power 6. Electron volt is 1.6 into 10 raised to power minus 19 joule. N is here the number of fissions. What is N, my future doctors? Number of fissions. In one fission, what is the energy? Do memorize this, do memorize this, do memorize this, important. Number of fissions is N. What is the energy in one fission? 200 mega electron volt. This is the joule. This much energy is there in one fission. So if they're asking you N fissions, so multiply by N, and N fissions is there in 1 second. So divide it this by time. So as soon as you're dividing the energy by time, what you're getting is the power. So what power is there? N by T of this much energy. And what power is given in the question? It's given 100 megawatt. So this is equal to 100 into 10 raised to power 6 joule per second. And here also this is joule per second. So N by T is required in the question, my students. So N by T can be calculated as 10 raised to power 8, this, divided by 6 minus 19, 10 raised to power minus 13. This is 2, that will be plus 2, and 1.6 into 2 is 3.2. Okay, so this 10 raised to power 8 divided by this entire numerical value of LHS will give you N by T. And what is N by T? N by T is number of fissions per second. See what we have actually done here. A small detail, uranium fission energy was there in our mind. We knew that and we solved the question. That's why I always focus on the detailed data, fixed data of nuclear physics. At least for NEET, it should be there in your mind. Okay, and I know this is already there in your mind. Okay, so moving to the next question. Next variety. If the speed of light were 2 by 3 of its present value, okay, so c is not the speed of light, students, it's 2c by 3. Then what would be fractional decrease in the energy released in a given atomic explosion? Okay, it means the energy released in the atomic explosion is related to speed of light. Obviously it is. That's called mass energy equivalent. E is equal to mc square there. E equal to mc square. So can I write E is proportional to c square? A is proportional to c square. Now according to question, E1 by E2 is c square. And what is the second speed? Second speed is 2c by 3. 2c by 3 square. This is 9 by 4. This is E1 by E2. Okay. Question is asking you fractional decrease in energy. Fractional decrease in energy. So first you see here. What is E2? E2 is 4 E1 by 9. Can you notice the decrease? Can you notice the decrease? and the fractional decrease means it was E1, then it became E2 as compared to E1. This is called a fractional decrease. This is the requirement in this question. So what is E1 minus E2? It means E1 minus this. This would be what? This would be 5E1 by 9 divided by E1. What will be this? This will be 5 by 9. So if you're changing the speed, that can be changed by various means. If you're changing the speed, its value is decreasing, energy is also decreasing, but energy is proportional to square of the speed, so obviously its decrease will be more. Okay, now moving to one more question and one more very interesting fact. See the question first. How much uranium-235 is consumed in a day? Time is given, that's why it's underlined. In an atomic powerhouse operating at 400 megawatt, provided the whole of mass is converted into energy. Basically, we are here assuming the 100% efficiency. Okay, although this is not ideal, still. How much uranium-235? First, let me see what is the total power here. Total power here is, my dear students, my future doctors, is 400 megawatt. This is the total power generating. Okay, this is again 400 into 10 raised to power 6 joule in 1 second. This much joule is there generating in 1 second. And what is the total time they're asking? Total time is a day. So what is the energy? We can calculate. Energy is power into time, isn't it? And what is the power with you? 4 into 10 raised to power 8. And what is the time? 1 day, 24 hours, 3600 seconds. So 24 into 3600 seconds. If you know the number of hours, that is 86,400. We can directly multiply them. 4 into 10 raised to power 8 into 86,400. This is the total joule, total energy. But the question is, from where this much energy has actually come? And this much energy here, it has come from where? From the conversion of the fuel. And what was the fuel? Fuel was uranium. Mass energy equivalence. What is the formula, my future doctors? E equal to mc square is the formula. So what mass of uranium you will converting here? E by c square. And what is E, assuming the 100% efficiency? What is E? E is with you is 4 into 86,400 into 10 raised to power 8 upon 3 into 10 raised to power 8 square. This is the mass of uranium that is being converted into energy to produce power of 400 megawatt in a day. If you will calculate this mass, you will approximately get 0.384 gram. Can you see what a small amount of mass you are converting? I told you a very interesting fact. This much gram mass of uranium. This is why uranium is so costly. Uranium, fissionable fuel are generally costly. This much uranium is giving you 400 megawatt of power in a day. Can you imagine this? So nuclear energy is so much of important energy. And the fuel we are using in this is uranium. This a small amount of uranium is giving you that much amount of energy. So this was this question. Now we have almost discussed all the concepts, but in our next class we will be discussing a detailed synopsis. This video, the synopsis video, that will be your revision video. If you will see one video, you will be able to get many key points, because it was quite an exhaustive journey of us, and we have done each and every detail of the nuclear physics. But one lecture we are going to discuss the synopsis. Be there, see this, and see if the entire nuclear physics is in your mind or not. If it is not, you can go with the particular topic video in detail there. Till then, study hard and don't forget 180 in physics, 720 in NEET. God bless you. Study hard. Happy learning. Bye bye.